There is a rule in science so fundamental it almost goes without saying. Nothing can be older than the thing that created it. A child cannot be older than its mother. A tree cannot be older than the soil it grew from. A star cannot be older than the universe that made it. Cannot. It is not just a rule of science. It is a rule of logic itself, of time, of cause and effect. It is the kind of rule that feels so obvious, so unshakable, that questioning it seems almost embarrassing. And yet, less than 200 light-years from Earth, practically our cosmic backyard, there is a star, a dim, pale, fast-moving star in the constellation Libra, unremarkable to the eye, invisible without a telescope, the kind of object that appears in catalogues as a string of numbers rather than a name. But this star has a name, a nickname, given by the scientists who study it. They call it the Methuselah star. And here is what the most precise measurements ever made of it, published in the closing months of 2025, using technology that didn't exist a decade ago, have found. It is 14.2 billion years old. The universe, by the most precise measurement ever made of it, is 13.8 billion years old. The star is older, by more than the entire history of human civilization, many times over. How is that possible? And what does it mean that a star sitting in our own galactic neighborhood appears to violate one of the most basic rules in all of physics? That is what this story is about. And the answer, if there even is one, reaches into the deepest, most unsettling questions in all of modern cosmology. Before we can understand what makes this star so disturbing, we need to understand what it is disturbing. When scientists talk about the standard model of the universe, they mean something very specific. Formally, it goes by the name LCDM, Lambda Cold Dark Matter. It is the cosmological framework that has dominated astrophysics for decades, a mathematical description of how the universe began, how it has expanded, what it is made of, and how it has evolved from the Big Bang to the present moment. It is, by any measure, one of the most successful scientific theories ever constructed. It predicted the existence of the cosmic microwave background, the faint afterglow of the Big Bang's heat, still detectable in every direction of the sky, and the measurements matched. It predicted how galaxies would distribute themselves across the universe on large scales. They do. It has passed test after test, observation after observation, for more than 30 years. And from this model, from the most precise measurements ever made of the cosmic microwave background by the Planck satellite in 2018, comes a number that has become one of the most important in all of science: the age of the universe, 13.80 billion years. With an uncertainty of just 20 million years, less than 0.25%, one of the most precisely determined large numbers in the history of human knowledge. And that number has a consequence. It sets a ceiling, a hard limit. Nothing in the universe, no star, no galaxy, no structure of any kind, can be older than 13.80 billion years, because 13.80 billion years ago, none of it existed yet. This is not just a theoretical constraint, it is a test, a check. If you discover something that appears older than the universe, one of three things must be true. Your measurement of the object is wrong. Your measurement of the universe's age is wrong. Or the model itself, the entire standard model of cosmology that everything else rests on, is wrong. HD 140283 has been forcing this question for decades, and in 2025, it got harder to dismiss. To understand why this star is so alarming, you need to understand how we age stars, because it isn't obvious. Stars don't come with labels. The key is a concept called stellar evolution. Stars are not static objects. They change, slowly, over immense timescales, but in ways that are mathematically predictable once you understand the physics of nuclear fusion and gravity. A star is born from a collapsing cloud of gas, mostly hydrogen. It ignites, and for most of its life, it fuses hydrogen into helium in its core. This main sequence phase, for a star like our Sun, lasts about 10 billion years. As hydrogen runs out, the star expands into a subgiant, then a red giant. Eventually, for low-mass stars, it sheds its outer layers and leaves behind a white dwarf. This journey follows a path that astrophysicists call a stellar isochrone. Stars of the same age, but different masses, will sit at predictable positions along this evolutionary track. By measuring where a star sits, how bright it is, what its surface temperature is, what its chemistry looks like, you can compare it against theoretical evolutionary models and estimate how old it must be to be at that exact stage of its evolution. But this method depends on two things: how precisely you can measure the star's properties, and how accurate your theoretical models of stellar evolution are. Both of these have a history of uncertainty with HD 14283, and that history is, in itself, a remarkable scientific story. There is also a newer method, one that only became applicable to HD 1400283 in 2025 for the first time. It is called asteroseismology. Stars, like bells, ring. Not audibly, but physically. Pressure waves travel through their interiors, creating oscillations in brightness that can be detected with a sufficiently sensitive instrument. These oscillations are not random. Their frequencies carry information about the star's mass, density, internal structure, and evolutionary state, in the same way that the sound of a bell carries information about its size and material. By detecting the exact frequencies at which a star oscillates, asteroseismology can determine stellar properties, including age, with a precision that other methods simply cannot match. In 2025, a team of astronomers used data from NASA's TESS satellite, the Transiting Exoplanet Survey satellite, better known as an exoplanet hunter, to detect solar-like oscillations in HD 14083 for the very first time. Combined with Gaia's precise distance measurements and ground-based interferometry, they derived the most accurate mass and age yet obtained for this star. Mass, 0.75 solar masses, more precisely determined than ever before. Age, 14.2 billion years, with an uncertainty of just 0.4 billion years. That uncertainty matters enormously. It means the most likely age of the Methuselah star is 14.2 billion years, and the universe is 13.8 billion years old. The gap between them is 400 million years, and the error bar on the star's age is 400 million years. They technically overlap, but only barely, just. And the central estimate of the star's age is still older than the universe. That is the problem that will not go away. Let's go back to the beginning. HD 14083 was not discovered with dramatic fanfare. It was catalogued, entry number 140283 in the Henry Draper Catalogue, an enormous systematic survey of stellar spectra compiled in the early 20th century. A number in a list, nothing more. But as the century progressed, it began to stand out. Astronomers noticed its spectrum was peculiar, metal poor, extraordinarily metal poor. In astronomical parlance, metals, means every element heavier than hydrogen and helium. The elements forged inside stars and scattered into the universe by their deaths. The more metal-poor a star is, the less of those heavy elements its birth cloud contained, and the less heavy elements present when a star formed, the earlier in the universe's history it must have formed. Before generations of stars had lived, died, and enriched the surrounding gas with the products of their nuclear furnaces. HD 140283 has a metallicity approximately 250 times lower than our Sun. That is not a small difference. That is the difference between a star born in the universe's first chapter and one born in a much later era. It is also moving extraordinarily fast. At roughly 13 million kilometers per hour, it is sweeping through our local stellar neighborhood at a speed that traces back to the galactic halo, the vast, diffuse, ancient outer region of the Milky Way, populated by the oldest stars, relics of the galaxy's earliest assemblies. HD 140283 doesn't live near us. It is just passing through, on an orbit that will eventually carry it back to where the oldest things in our galaxy reside. Astronomers have traced its origins to a dwarf galaxy that fell into the Milky Way and was torn apart and absorbed long ago. HD 140283 is a survivor, a star that formed in another galaxy entirely, before that galaxy even knew it would one day become part of ours. All of this pointed to extreme antiquity, but by how much? The history of attempts to pin down this star's age is a story of science working exactly as it should, and exactly as it is supposed to. Imperfect measurements giving way to better ones. Alarming results being examined, challenged, and refined. Around the year 2000, using the best available measurements of the star's distance and stellar evolution models of the time, estimates for HD 1483's age were coming in at approximately 16 billion years. 16 billion, 2.25 billion years older than the universe. Not barely older, not within measurement uncertainty, 2 billion years older. If those estimates were right, the standard model was not just slightly wrong, it was catastrophically wrong. Astronomers pushed back. They examined every assumption in the calculation. Distance measurements from the Hipparcos satellite introduced uncertainties. Chemical abundance measurements, critical for placing a star correctly on evolutionary models, had their own error ranges. Nobody was ready to declare the standard model dead over a single star. In 2013, NASA's Hubble Space Telescope stepped in with its fine guidance sensors, instruments designed to measure stellar parallax with extraordinary precision. Parallax is the most direct method of measuring a star's distance. By watching it shift against the background sky as Earth orbits the Sun, you can calculate exactly how far away it is. Hubble pinned the distance to HD 14283 at 190 light-years, more precisely than ever before. With that improved distance, the star's intrinsic brightness became better known, and with better brightness data, the age calculation changed. The result? 14.46 billion years, plus or minus 800 million years, still older than the universe. But now within the error bars, the lower end of the uncertainty range dipped below 13.8 billion years. The embarrassment was reduced, just barely. The paradox was softer, but it hadn't gone away. Then came 2021. A new analysis using physical radius measurements from interferometry at the Chara array, where the actual apparent size of the star on the sky is measured, combined with updated stellar evolutionary models, produced an age of 12.0 billion years, plus or minus 500 million years. 12 billion, safely younger than the universe. Problem solved? Not quite. Because the 2024 analysis, applying different assumptions about the star's chemical abundances, pushed the estimate back up to somewhere between 12 and 14 billion years, depending on which chemical measurements you trusted. And then came the 2025 asteroseismology result, the most precise measurement ever made of this star, using a completely different and more physically direct method, 14.2 billion years, plus or minus 400 million, back above 13.8 billion, right at the edge, pushing. After decades of refinement, the most modern technique available, listening to the oscillations inside the star's own heart, says it is, within measurement, older than the universe, or at least as old as it. Before we spiral into panic, it's worth being precise about what this number actually tells us, and what it doesn't. The 2025 age of 14.2 plus or minus 0.4 billion years means the true age is very likely somewhere between 13.8 and 14.6 billion years. That lower bound, 13.8 billion years, is exactly the age of the universe from Planck. So there is a scenario where HD 140283 is 13.8 billion years old, and the universe is 13.8 billion years old, and everything is fine. The star formed almost immediately after the Big Bang, within the first few 100 million years, when the primordial gas was still cool enough to collapse into the very first metal-poor stars. That's not physically impossible. The first stars are thought to have formed within a few 100 million years of the Big Bang. A star forming at 200 million years post-Big Bang and surviving to today would be 13.6 billion years old, slightly less than the universe's current age. Plausible. But here's the uncomfortable truth. The central estimate, the most likely value, is 14.2 billion years, not 13.8. And the error bar, while it includes 13.8, centers on something older. There are really only a few ways to resolve this cleanly. Option 1. The stellar age measurement is still wrong. Some systematic error in the asteroseismology, in the chemical abundances, in the theoretical models, something we haven't fully accounted for, is pushing the estimate upward. Possible. Scientists take this seriously. Option 2. The age of the universe is wrong. Not by a lot. The Planck measurement is extremely precise, but even small revisions to key cosmological parameters could shift things. And this is where an entirely separate crisis in cosmology becomes relevant. Option 3. Something about our understanding of very early star formation is incomplete. Stars may have been able to form earlier than our current models predict, in environments and conditions we haven't fully characterized yet. None of these options is comfortable, and all of them are currently being debated, actively, by the world's leading cosmologists. HD 140283 does not stand alone. There is a deeper, more pervasive crack running through the foundations of modern cosmology. A crack that has been growing for nearly a decade, that no one has been able to fully explain, and that may or may not be connected to the age paradox of the Methuselah star. It is called the Hubble tension. The Hubble constant, named for the astronomer Edwin Hubble, who first measured the expansion of the universe, describes how fast the universe is expanding. Specifically, how much faster a galaxy appears to be receding from us for every additional megaparsec of distance. It is measured in kilometers per second per megaparsec. For a universe described by LCDM and calibrated against the cosmic microwave background, the Planck satellite gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Very precisely determined, one of the most important numbers in cosmology. But there is another way to measure the Hubble constant. Rather than using the early universe's afterglow, you can measure it directly by observing Cepheid variable stars and Type 1a supernovae in nearby galaxies, using them as standard candles whose true brightness is known, and measuring how fast those galaxies are receding. This method, called the distance ladder, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. 73, not 67. A 6-unit gap, which sounds small, but these are not estimates riddled with uncertainties. Both measurements now have error bars far smaller than the gap between them. The two methods are measuring the same physical quantity and getting significantly different answers. This is the Hubble tension, and it has defied explanation for years. Why does it matter for the Methuselah star? Because the Hubble constant and the age of the universe are directly connected. A higher Hubble constant means a faster expansion rate, which means the universe has been expanding more vigorously and is therefore younger. If the true Hubble constant is closer to 73, as the distance ladder suggests, then the universe might be somewhat younger than 13.8 billion years. And a younger universe makes the Methuselah star's apparent age even more paradoxical, even harder to accommodate. But if the true Hubble constant is different, if there is some physics we're missing that affects the expansion rate at different epochs, then the universe might actually be older than the CMB measurements suggest. Old enough to contain a star like HD 14283 without any contradiction at all. The Hubble tension is not a solved problem. It is the most debated, unsolved problem in observational cosmology, and every measurement of an extremely old star like HD 14083 makes that debate more urgent. And if that weren't enough, the James Webb Space Telescope has found something that pushes even harder on the same foundations. When JUICE began returning data from the early universe, galaxies seen as they existed hundreds of millions of years after the Big Bang, astronomers expected to find young, primitive, dim structures, the first cautious assemblies of gas and dark matter still building themselves up from raw material. What they found instead was galaxies that seemed fully grown, massive, luminous, chemically evolved, and extraordinarily numerous, far more of them than models predicted should exist at that age. In some cases, the models were off not by a factor of 2, not by 10, but by orders of magnitude. Galaxy after galaxy, survey after survey, showed a universe that had managed to pack an enormous amount of star formation and galaxy assembly into a time frame that, according to LCDM, should have been far too short to produce what was actually there. A paper from the Instituto de Astrofísica de Canarias analyzed used data of galaxies from the universe's first few 100 million years, and found some of them appeared to be older than LCDM's age limit allows. Not all of them, not most of them, but some. And those outliers are the ones that demand explanation. Combined with the Hubble tension and the Methuselah star problem, JUICE is drawing a picture of a universe that keeps producing things that seem too old, too massive, too evolved for the timeline the Standard Model provides. Is the Standard Model wrong, or are we systematically making errors in our measurements? Both possibilities are frightening in their different ways. Let's sit with this carefully, because the options on the table are not all equally radical. The first possibility, and the most conservative, is measurement error, that despite the sophistication of modern asteroseismology, and despite Gaia's extraordinary distance precision, there are remaining systematic errors in our understanding of HD 140283's chemical abundances, or in the theoretical stellar evolutionary models we compare it against. A different assumption about the star's oxygen abundance, for example, can shift the age estimate by 1 billion years. These things are not trivial to pin down, even with the best instruments. The second possibility is that our measurement of the universe's age is slightly off, not because the Planck data is wrong. It isn't. But because the physics we're using to interpret it might be incomplete. Dark energy, the mysterious force driving the universe's accelerating expansion, is currently modeled as a cosmological constant, a fixed, unchanging property of space. But there is growing evidence that dark energy may not be constant. If it has varied over cosmic time, stronger or weaker at different epochs, then our calculation of how long the universe has been expanding, at what rate, and for how long, could be subtly miscalibrated. The third possibility is the most radical, that the Standard Model, LCDM, is fundamentally incomplete, that there is new physics we haven't discovered yet, physics that changes the early universe's behavior, or the way dark matter interacts, or the way expansion proceeded in the universe's first billion years. Some alternative cosmological models, such as the CCC plus TL framework, covariant coupling constants plus tired light, suggest the universe could be as old as 26 billion years. That would easily accommodate HD 140283 with no paradox at all. And it would explain the Just galaxy findings, the Hubble tension, and the Methuselah star in a single stroke. These are not fringe ideas. They are published in peer-reviewed journals and taken seriously by serious people. They are also far from proven. What they represent is the edge of our knowledge, the frontier where measurement precision has outrun our theoretical understanding, and where the next great discoveries in physics are most likely hiding. Let's step away from the numbers for a moment and think about what this star actually is, what it experienced. HD 140283 was not born in our galaxy. It was born in a dwarf galaxy, a small, primitive collection of gas and dark matter that existed separately from the Milky Way in the early universe, when the cosmos was perhaps only a few 100 million years old. The gas from which it formed was almost pure hydrogen and helium, the first and second elements, the only ones that existed in meaningful quantities before the first stars lived and died. This star is a direct product of the universe's first chapter. Its atoms, the hydrogen in its core, the trace heavier elements in its outer layers, were assembled within a few minutes of the Big Bang. The hydrogen nuclei that fuse in HD 140283's core today were formed in the universe's first 3 minutes. At some point, billions of years ago, the dwarf galaxy that gave birth to this star was torn apart by the Milky Way's gravity, shredded into streams of stars and gas that were absorbed into our galaxy's halo. HD 140283 survived that merger, and it has been orbiting through the Milky Way ever since, on a looping path that brings it periodically through our local neighborhood before swinging it back out to the halo. We are, right now, in one of those passing moments. This star formed in the first era of star formation, the cosmic dawn, when the darkness of the early universe first broke. It has watched every subsequent generation of stars form, burn, and die around it. It was ancient before our sun was born, before the earth was a thought, before the atoms that make up every living thing on this planet had even been forged inside a stellar furnace. It is, in the most literal sense, a relic of the universe's very beginning. And it is 200 light-years away, close enough that the Hubble Space Telescope could measure its parallax with fine guidance sensors, close enough that TESS could detect its oscillations, close enough to be part of this conversation. Here is the thing that makes science different from almost everything else. It doesn't retreat from paradoxes, it runs toward them. When Newtonian physics produced results that didn't match the observed motion of Mercury's orbit, it wasn't swept under the rug. It was studied, debated, and eventually resolved by a deeper theory, general relativity, that explained not just Mercury, but everything Newton's framework explained, plus everything Newton's framework couldn't. When the Michelson-Morley experiment failed to detect the ether, the medium through which light was then thought to travel, it wasn't dismissed. It was the crack in the foundation that eventually led to special relativity. Every time a fundamental measurement doesn't fit the reigning model, that misfit is not a failure. It is a signpost, a door, a marker saying, the next level of understanding lives somewhere behind here. HD 14CDU283 may be that signpost. It has been pointing at something for decades, something about the early universe, about the age of the cosmos, about the completeness of LCDM. That hasn't fully resolved. The 2025 asteroseismology result, which produced the most precise age estimate ever made for this star, didn't solve the paradox. It sharpened it. That sharpening is valuable. The more precisely we can define the problem, the more precisely we can locate its solution. Each new measurement constrains what can possibly be true. Each constraint narrows the space of viable theories. The Gaia satellite continues operating, refining its parallax measurements of nearby stars, including HD 140283. Future data releases will further reduce distance uncertainties. Ongoing US programs are adding to the dataset of ancient galaxies that seem to challenge the timeline. The Nancy Grace Roman Space Telescope, launching in August 2026, will survey the universe in ways that may further constrain or challenge the standard model. Every piece of data is a vote, and right now, the vote is close, but leaning towards something being subtly, importantly incomplete about the way we understand the universe's earliest moments. But there's a question even deeper than, is the standard model right? It's this: how do we know anything about the age of the cosmos at all? This is not a philosophical dodge. It's a genuine scientific question. We can't travel back to the Big Bang. We can't watch the universe age in real time. We can only infer from the behavior of light, from the properties of stars, from the oscillations of ancient stellar interiors, from the faint afterglow of primordial heat, what happened and when. Every measurement is a chain of reasoning, distance to a parallax, parallax to luminosity, luminosity to evolutionary stage, evolutionary stage to age. Each link has uncertainties. Each assumption introduces the possibility of systematic error. And yet, and this is the astonishing part, these chains of reasoning, built from different starting points, using entirely different techniques, converge on roughly the same answers. The age of the universe from the CMB, the age of the universe from stellar evolution and asteroseismology, the history of the cosmos from the distribution of galaxies. They don't perfectly agree, but they roughly agree. They're in the same ballpark by factors of less than 2, which, for measurements spanning 13.8 billion years, is extraordinary. The fact that there is a tension, that HD 140283's age nudges above the universe's age, that the Hubble constant disagrees, depending on how you measure it, is not evidence that we know nothing. It is evidence that we know almost everything and are now close enough to the truth that the remaining discrepancies are small enough and our measurements precise enough to see them clearly. We are in the era of precision cosmology, where the errors are small enough to notice. And that is exactly when the next great revolution in understanding becomes possible. There is a star, 200 light years from where you're sitting, that is older than the universe should allow. It formed when the cosmos was barely an infant, from gas that was almost pure hydrogen, in a galaxy that no longer exists, in an era before planets, before the elements that make up living things had even been forged. It has been traveling for billions of years, through the ruins of the galaxy that made it, through the outer halo of the Milky Way, through stellar neighborhoods it passes through on its enormous, looping orbit. And right now, at this precise moment in cosmic history, it is in our neighborhood, visible through a telescope from Earth, close enough for our most precise instruments to listen to its heartbeat, to count the oscillations in its interior, to translate those oscillations into a number, 14.2 billion years, a number that doesn't quite fit. And that not quite fitting, that small, stubborn, precisely measured discrepancy, may be one of the most important things anyone has ever measured. Because science doesn't advance when everything is tidy. It advances when something won't fit, when a number comes back wrong, and the wrong number has been checked and checked again, and keeps coming back the same way. The Methuselah star is that wrong number, and somewhere in the explanation for why it won't fit, whether the answer lies in our understanding of stars, or the age of the universe, or the physics of the early cosmos, lives the next great chapter in our understanding of everything. We just have to be patient enough and precise enough to find it.